Okay. Try to get some things set up, but all right. So what are we doing today? Today the goal is effectively to work a little bit on Heka.jl, specifically trying to go through and change some of the just the quaternion algebra functionality. So if we go in here, I forget what version I'm on. It's been a little bit. I had a friend visit, so I have to kind of remember just a handful of commands. Also think about my move. So last I remember is we implemented some characteristic 2 aspects into the quaternion algebra types. And then we started actually working on explicitly, at least, we started working on changing all of the central subalgebra types into actual central subalgebra types. So things like matrix algebras, quaternion algebras, those are now certain structs inside abstract central subalgebras. And we're trying to separate out like reduced traces and reduced norms from everything else. So I think what I'm going to do is keep on going through what I think I'm going to do is keep on going through. I wonder, did I change this? No, I didn't. Anyways, that works though. I'm going to keep on just developing the central subalgebra type and then see what actually needs to be changed. So unfortunately, it's been long enough that like I've forgotten kind of everything that I was working on or have done. I don't need to run anything. So where were we? Okay, like this is still in here, group algebra elements. I think I just I think the last thing that I may have done was copy this file actually. So there's the same file, right, in abstract associative algebras. Some things are changed already, but a lot of it is still the same. So like the binary operations should still be like operating on associative algebra elements. We do want to change that. One other thing is To what extent does the central simple algebra type have a good definition for elements already? So a central simple algebra element should just be a pair of central simple algebra and some essentially element in that parent object. And where would we have implemented this? In the types file? That makes sense. So we've got abstract central simple algebra, abstract central simple algebra LM, quaternion algebras. These are subtypes of the abstract central simple algebra type. Mutable struct, central simple algebra element. Yeah, so we have parent and we have coefficients given to us in the form of a vector. And just different ways to construct elements. So we're either operating on, so just like calling kind of constructor on the algebra itself. Why the fuck is this different? Okay, this specifies a new object of parameterized by T and S. Parent of this element should be A. The coefficients of this element are going to be vector of type T, which should be the base field essentially. That makes some sense. It's going to be a vector initialized with undefined entries, and then let's see, size of the multiplication table. So that's specifying the number of, and then this one function I'm not sure about, but oh, it's like n by 1, where n is the size of the multiplication table. So you have to specify all the coefficients of basis vectors from A. And then we're going to go over some loop, and then what do? We specify the ith coefficient to just be 0, and then we return z. It's a bit weird. Here, why is this different? So we're input a quaternion algebra with some parameterized element type T. So that's the base ring again. S now is not relevant, right? Unless it's different here. And then we initialize a new element T, and then the quaternion algebra right of type T. Okay, we should look where we actually end up calling this thing. Does this mean, for example, so I think that this is to some extent capturing the structure constant algebras and matrix algebras, which means if I go to matrix algebras, then the struct for these should have multiplication tables in their definition. I guess that's still in here. So mat alg enter. I gotta get used to changing these. So these still are multiplication tables. Interesting. Okay. Okay. All right. I can maybe vibe with it. So where was I? In here? I guess I wasn't in here yet. We were still just going through types. So I didn't even have to scroll that far. It's pretty funny. So every time we want to create a new central simple algebra element for some new type of central simple algebra, we'll have to come back and kind of add it to this list. The last one calls, let's see. So this is like structure constant algebras. This is like quaternion algebras. I guess matrix algebras also fit into this type. And then if we call central simple algebra element on some central simple algebra coefficients of some vector of type t, then we just input the coefficients. That's fine. It seems wrong to me. But I don't have any actual concrete reason to say this. It just seems wrong to me to have, and I guess this is the whole point. Never mind, it's fine. It seems wrong to seemed wrong to me to have like functions of one input, two inputs. But that's fine because you're specifying the type, so it's a new instantiated function every time you want to call it. All right. Let's see. We're gonna ignore some of this stuff right now. And I think this one should be yes in some sense, right? Is simple? Yeah, it's gonna be simple. Why is this not always going to be true? Is that because we allow ring inputs? It's like just change that shit to a field and let's call it good. We can also do quaternion algebras over a ring. That's fine. Is simple 1. Is simple. Let me just check just to make sure, but these should create matrix algebras of size n by n. Oh, it's kind of crazy too, because you're allowed to create. Oh no, because you're allowed to create matrix algebras over non-commutative rings, huh? Could just add that in as a little if. I don't know when this would not be simple for an algebra. R, it's like it's not simple only if R is not simple. So, but then the same justification is true here, right? So like, why is a quaternion algebra returned as simple if base ring is not? So I think it's fine to have it be a ring as input. Just know that like you should only be entering in fields for quaternion algebra, just in general. Could check if the type of the base ring is a field. So I think this should be changed. So what the fuck just happened? We're gonna keep on going. How did that? Let's quit and not save. I want to see what happens to the file. Is there some kind of macro on that already, or am I just crazy? Oh no, as simple as stored, isn't it? Oh, okay, that's fine. This should be if R as type field, then as simple as yes. And otherwise, it's not. Also, I guess it doesn't like R. That makes sense. I don't know why I wrote R. If the type of T is a field, I guess. And I wonder if this statement actually evaluates out as true, right? So I don't know what this actual statement does. Okay, otherwise we should return 1. Sorry, 0. Guess this is just a type assertion. Is a type, or we could do this. So So if this, so this is fine. Should be the same down here. So it is simple. So if we initialize a matrix algebra, for ring R, base ring and coefficient ring is weird as hell. I'm not sure what coefficient ring is even supposed to mean for a matrix algebra. You create a matrix algebra. I don't think there's any documentation on what the coefficient ring is supposed to call. So let's just check just in case. The projects. I also switched recently to Zen, and I wouldn't have known where the documentation is for this project in the first place, but just trying to find my way around is also another hurdle now. So let's see. Search matrix algebras. And we went to morphisms. What did I search? Could be that the coefficient algebra is actually defined inside the matrix algebra or the structure algebra type. We can try checking that. It's not. Is that not true? Yeah, okay. Coefficient ring, coefficient ring. I'm not sure what this does, so okay. We'll just go back in and try to figure this out. Okay. This one I feel pretty confident about. Having this be 0 must be don't know, and 2 is no, right? It's not clear why that would be true, but just in this code base, I think that is true. There must be a better way to do that. Alrighty. Let's just ask Gemini. If I store a value in a struct for a property of an object that should take on 3 things, true, false, and something else, I don't know, what's the best way of doing this? Could have something like, I don't know, like if there's like enum, enums, like enumerate some stuff, so then we could have a true object, maybe true, false, and could be missing. Type for your struct field should be union bool missing. The missing object is specifically designed to represent information that is unavailable or unknown. So missing is an object. Oh, I'm already in the terminal. Missing. Missing. What the fuck? Value nothing is typically used to indicate the absence of a value. For example, a function that might not return anything, whereas missing is for when a value should exist but is not known. Unlike missing, nothing doesn't propagate through logical operations and will usually throw an error, forcing you to handle explicitly. Oh, but missing has the false, and missing is false. That makes sense. True and missing is missing. That also makes sense. False or missing then should be missing also, right? So if I did like, okay, great. Okay, then this should be totally restructured, right? It just doesn't make any sense to have this be an int, I guess. Things like this, right? Int, that should be just Boolean or missing. But that's gonna fuck up so much, I imagine. I don't even know where you'd find, by the way. I mean, something like this, right? So like, okay, wait, is this just because, I don't think that this is true, maybe, but it seems like it is. So, alright, I'm just probably a novice. Okay. So it's just because in Julia, false is 0 and 1 is true, that we're using 1 as placeholders here, and then missing is 2. Missing is not obviously 2, but I think that's probably fine. If I return type of true, I get 1. Type of 2, I get in. Okay. Okay, I'm back. I was just thinking about this, having at some point, one of the first things I want to do is actually go through and change this. Because didn't we just check? Right. Okay. So it feels like don't know should be 2, and then false should be 0. All right. So we'll go back and put it on the to-do list. So the one thing that we should get done is probably as soon as possible we should get done just changing this, and then we can fix it, and then we'll go back and try to fix the other things if we can. So 1 is true. 2 is I don't know. Okay, so either return 1, that's true, or return 0, that's I don't know, even though 0 is false. What else did we have? So it was the same for matrix algebras. So if T is some, or if R actually. Right, so what is T and S here? Let's see. Okay, T is some, looks like coefficient ring. It's going to be the base ring. Okay, it's going to be the base ring, not coefficient ring. We've got different things here. And S is going to be a matrix element. So this is like pulling in I think that's Julia's native type. So, so matrix element, or maybe it's not. Maybe it's abstract algebra or something. But we can ask Gemini, do a little quick search, and then go down here. So if R is type field, so mat LM is a Nemo type. It's kind of interesting. So I'm not necessarily sure why you would parameterize these matrix elements based off of Nemo matrix LMs, unless you were making the matrix algebra elements as being mat LMs. So if it's field, then the answer is that it is simple, and if it's not a field, the answer is that we don't know. Is semi-simple. That's still, it's not clear. It is clear if A is a field. Commutative, it's not so clear. Coefficient ring. This constructor really doesn't make any sense to me. So let's just try it out, see if it actually comes up as a Nemo object. So we're going to do using Heka. I don't know if doing that while pre-compiling was the best thing, but I don't know if that came from actually just what I just did. Again, just in case. Don't know why these two things are different. I think that coefficient ring, okay, it could be actually that coefficient ring is somehow okay, it could be for some compatibility thing. That should have been maybe mentioned though. So let's try just creating a matrix algebra. How would we do this? So if we enter a ring R and S, a non-commutative ring, it returns the n by n matrices over S considered as an R algebra. That makes sense. So that's what this is doing. So the coefficient ring should be, in this case, it's the components of the matrix, okay. And then the base ring is the algebra structure. Okay, that makes sense. Kind of want to just say like yeah, God, I don't know, leaving comments kind of does suck. So this one was actually good documentation and showed up actually trying to search it, so maybe I won't change anything. Okay, so if the base ring is a field, that's fine. And here, how do we determine this? It's really, I mean, we could determine it if R2 was a field. Actually, one way that you could determine it is if R2 is simple. Just, you only know that, so there's probably no general call for is simple. Probably non-commutative rings in general don't. You don't know that? Okay. Okay, let's try going back. Okay, what do we got going on here? So if we have an absolutely simple number field called on an abstract central simple algebra LM with coefficients in abstract simple number fields. Got some crap. QQ field. Have some crap. I don't think we need this anymore. This is one thing that I was thinking. So God damn it. It wasn't in here, was it? It was in here. I think that was fine. Let's undo it for the moment and just try testing it in Julia. What would I try doing? So what I would try doing is something like this. Okay. So that doesn't confirm or deny anything, to be totally honest. I don't even see why that was okay, I'm gonna leave it. It didn't seem alright. I'm not even gonna think about it. It's out of sight, out of mind. Function 1. Unary operations. So we're back to here. I feel like there's ways to just like copy something like that and then just have so like if I do it again though, right? Too bad. I don't think that's how it's supposed to be though. In terms of how do I paste like multiple times? There's definitely a command for this. So goddamn. It's been a little bit, obviously, since I've been on my computer. Yeah, this is not what I wanted. So I think it might just be Shift P. Or it's yank yank. That's not right. So I think I can do search help yank. I was there, I know, and then I fucking moved it. So let's see. So what is YY? It just shows up here, yank some number of lines into the register. So let's see. Where's my cursor? Where's the focus? It's just capital P, right? Okay. Fuck. Wait, I actually wanted that. Oh my god, I am just fucking this up. That is unbelievable. That looks fine to me. I could just find associative algebras, but I think it's probably okay that I'm doing this. Okay, if I capital P it, kind of makes me worried that there's some T's around that should have been like you think that capital P would switch the order of where you put it, either to the left or to the right of the cursor, but maybe it does and I just haven't been paying attention. Okay, this I don't think I need. I fucked that up a little bit. So delete that. This too. Delete that. Leave some of this. So delete. Delete. This looks fine to leave. I actually don't know how these are called. I don't know how these are called in like in the sense that okay, so let's just read it. So if we take let's see, B and A are going to be abstract associative algebra LMs, and C is an abstract associative algebra LM. They're all actually parameterized by the same type. Then we check if A and B and C and B have the same parent. We make sure they all have the same parent, and then what do we do? So if C is A or if C is B, then we just do what? D is just call the parent, so that's 0, and then we say 0 is add of this. Okay, so what does this function do? Return a plus b. It's not clear. I don't even know if I can call this. I want to know what arguments the function takes. Maybe I can just do dump. Add. Function of type of add. I think that if it's true that this is just adding these things up, like vectors, or calling basically plus on each of them, then I can just delete this. Okay, so there's a bajillion methods for this. Alright, I'm not sure if I should change these yet, I guess. Seeing that there's like a bajillion other methods to find for this operation is kind of whack, honestly. It's kind of crazy. Like, what does this call even do? So this is if B is of type T. That's fine, but what if C, B, and A are all of the same type? What if they're supposed to be the same object? Then what do? We call add on a triple of things where one of them is 0, so that's going to go down to some other call where one of them is not 0. Is that true? And then for some range, what is this? I didn't know that you could index like this. I think because you're just calling this on the coefficients, you can just ignore it, honestly. Yeah, let's just delete it. Fuck it. Let's make sure that the 0 actually returns 0. I think it's probably fine. Eventually we get to here, and then it's actually important again. Then what is this? Because this actually was referencing mul. And so we call star on essential simple algebra. I kind of think these operations are fine. But I can test it. If it turns out that they're not, then I've learned something. That's good. So why do I think that it's fine? Just to clarify for myself. I think it's fine because it looks like these add mul functions are being called in such a way that they rely on the implicit operators for the objects themselves. So I just think that if the function calls, then if it passes in like essential simple algebra LM, what's going to happen is it will see that there's no such function for essential simple algebras. It will go to the next type, associative algebras, or abstract associative algebras, and then it will run the add mul or mul bang functions, and the inside of those should be totally valid operations that will eventually return again essential simple algebra, but I could be totally wrong. So we're gonna just try with Q is gonna be a quaternion algebra, and I don't remember the inputs for these, so I think it's field, and then just like these things. We're gonna say I is Q, so we have I's. Oh, because I don't have the expressify on. Maybe almost better, honestly. So I squared, error. Shouldn't be a problem though, right? So No fucking way this is the order. Okay. Well, that was equally confusing. Okay. What is another type? Like big int? Is that of type int? Is int of type big int? Neither of these are comparable. Okay, that one makes sense. And it's the same, I mean, it would be so fucking crazy if that wasn't true. Okay. If they had like swapped the caret in some sense, or swapped the subset. So I don't understand why this actually doesn't run. It's because in the function call you assert the type. That's it, right? So here you're asserting that the type needs to be associative algebra. Holy shit. Okay. So then we have to define all of this. So I needed to have those functions. That's fine. I think I can just undo it. So undo essential simple. And now I have to do all of this again. Oh shit. Because it probably is central simple algebra LM, but have I been doing that this whole time? This is the only instance? No, there's 3 of them. I think I could have just replaced, but... Now I also need to figure out what this does. Seeing shit on the same line is so annoying sometimes. Even though it indents. think that I could probably macro that away, but that's like one of those things that you just kind of live with, right? And learn. Okay, I'm ignoring this for the moment. God damn it. Okay, now I don't need this. Okay, I'm gonna ignore stuff after division for now. And just see if fuck. How'd I end up banana? Man, I'm just dying today. Let's try this. Try to set a quaternion algebra. Try to set an element. Set another one. And then we'll try 1 times I times j, and kind of disturbing. I just haven't gotten there yet, I guess. there's some things. Oh god damn it. There's some things that I still need to go through, it looks like. I mean, there's a ton that I still need to go through, but even here, we just did binary operations. We haven't gotten to, you'd call exponentiation a binary operation, right? Ad hoc operations. Things like this. Dot is kind of a weird one. Oh no, dot is the opposite algebra? No, this is weird. So inverse makes sense that you have to do it before exponentiation, I guess, because you also want to have that in there. Shouldn't be binary operations then, right? Because there's a bunch of binary operations down here, like this is a binary operation. I guess it's not binary on the same. I guess those are binary operations on the same elements. Okay, I kind of believe it. Okay, parent object overloading. We get rid of the group algebra. And then we have to change the string IO. I imagine this is why some things were and weren't showing up. Like multiplication for some reason was showing up. That almost makes me feel like it's actually doing something weird, but just making an element actually doesn't print. Okay, there's like a bajillion things to do still. Fuck. Why is this in here? Some of this shit should get moved out, I think. Calling like reduce trace, for example. I don't think that should be like an inherent natural thing to the element type. Or am I wrong? Should we have functions that are inside that operate on elements, and those functions stay in this file? Conversions, change ring, decompose, ideal map. It's really not clear. Okay, it's just not clear. Okay, well, that's it. I'm gonna call it. So I'm tired as hell. Gonna go sleep. Maybe do this again tomorrow.